recording. Guys, I need to find a way to do it properly. If this is not recording, that must mean, this should not be recording. Let me just clear this recording here. So this is speechnotes.co, which is where I get my transcript from. It's recording now. That must mean I'm doing it right. So basically, guys, it's very, very important, to not miss this video. I want to give you what I'm trying to really achieve here. I want to give you 3 implementations before I start anything in any way, shape, or form with my video. So basically, so guys, if you guys don't understand anything this video, I'm surprised that you are thinking like that. But if you really watch the first video and the second video, but try to take away something at the bare minimum. If it's just one thing, one word, one word to remember, that's not character. Please have that word from this video. Okay, guys, what's the video? Rift stage 2. So we're talking about the parser stage, but the goal is to bootstrap it. So like an elf, basically something that's elf, executable and linkable format. It's really can run itself. It's a bootstrap of itself. It's like basically like a palindrome. So basically, if you have the text palindrome, a palindrome is just a word. But you got the palindrome of pat, tap. Guys, I'm giving an example, but pat and tap are what? Are both words. So what you got there is a word program that recognizes palindromes. I'm gonna give you this example, continuing with what I really was doing there. So why does this matter, guys? We did talk about the 2x2 matrix for the system coherence, but this video is important because Rift program should just any single one program can should boost itself, because it can match. If your program cannot boost itself, it's not a Rifty program, guys. You need to do more run more Rift tests. The Rifters are watching you with the kind of weird eyes. Guys, Rift is flexible, guys. I'm really happy I give you guys this. So basically Rift. Basically this is a Rift. It's gonna be written in Israel Gotilang, and this is Guinea. Basically this is Parrot Guinea. Say hi to Guinea, guys. It's not animated here, this guy, but it's a Igbo parrot. Basically, Guinea is just a marker. It's just a Gotilang programming language marker. It's my heart there. They're very important. It's my war. Okay. Anyway, so my war program. What's my battlefield and battleground focus on? Look like a human being now. So basically. I want to say to you guys, after showing this rotation, you will never want to go back to Yak. If anybody want to go back to Yak, it's not my problem. You can go back to Yak, compiling. I don't like I never did. So without further ado, let's start. Okay, go here. Oh, basically, this is the program here. Open is open. I'm gonna try to create another one called basically it's got Brave Bridge. Open. This is a program you can download with Git clone. You can go here, code, download the zip. And then you can extract the zip and then run the exe. But here you get the programs here. I won't even go through the programs here with my editor, but this way I can go through the programs. This is the flex application. This is open. Basically, this is to open any PAL using the 8x8 encoding, which is octal. Bound 16. So you get 8 plus 8, 16 hexadecimal. If you don't convert to 4 byte segments, 8 byte segment, but the alpha and variable space in 3 bytes sequential, so it can't be 8 or 8 or 12 by 12. Basically, I'm moving this wrong. Let me try the calculator. So basically, it has to be like at least 3 bytes you store, or 3 segments at the minimum, which is 3 by 3. For example, I've started this now. This is Rift. This is world's first partition of the system that works the way I want it to. So you get 16 per octal, and 16 divided by 4 is what? 4. Now that 4 bytes is good. 4 bytes of memory, because that's you get 2 plus 2, you get 4. That's the minimum for 2 states bits. But 2 encoding bits, you need a 1 or 0, making it a 1 0. But you can create a 4th one, which is 3. So you need 3 minimum for any system. So if you're doing little endian or big endian, doesn't matter. But this is just the system really envisioning for the freedom of programming development. So if I have 2 plus 2, that's 2 states I can be at any one state can be in any 2 times. Basically, any program can be in 2 states at once based on parallel execution. But if one program is doing parallel, you can do 2 at once. That's 4 states, 4 qubits of encoding. But then that 4 and 2, basically, if you can do 4 and 2, other people can do 2 plus 2, and do a 4 more, based on things that interact. That's 2 plus, making 8. So it can be a total of 8 states. 16 bytes can be, but you don't get 16 times 8. But basically, what's my thing? I'm doing so poorly, guys. Oh my days, this is just so I have it here. I did bring it here, something. Did I? So basically, let me get to the point. One thing to share with you guys, you guys should have this interpretation. If anything else, you don't understand the source. This is an ELF interpreter. So it's basically matches here. So you can see here, you get U38 key value priority. Now the priority defines how the system evolves based on the pointer value. But what that means is you get 2 pointers to data, a little endian and big endian, and you get them at both ends of the Rift pattern syntax. But this is not actually the Rift system in the full development, the full scope of things. Because it's conscious, guys, I want to say it's conscious programming. It knows what it's doing. It knows. And that's the beauty of the thing. So I'm doing a quotation now. So what I'm saying to you, what this means basically is you get a Rift token memory, a Rift token value, and what's a Rift token? This is given the type, polarity, and reverse. So this reverse is the bit flip, the bit size. So if you have the encoding polarity sequence that mean different things, but this just creates a rotated left and right. So this is like a rotation function that uses the R syntax to do it. But this creates a DLL for main C. You can just execute. If you compile this code, you get something called R open. Now you guys can get this and take a file, any file you want, any file that's an image file, a PNG file, anything you want, and you can use this to pass some parameters to it. So this gets 1D to 3D. So this is just what it is. Basically you can define any state machines as a linked list, and you can if you don't think about it in code as 1 to 0, the linked list contains only 1s and 0s, but the head pointer is the start. But that head pointer has to be the other one. So if you have a start pointer as a 0 or 0, you have 0 or an ELF, like a start, no start state, empty state. You have something or an epsilon state. You have the other one, the other reparator one, the inverse, which is the start with the opposite, start from the opposite end as if it starts. That's how linked list works. So if you're doing like a kind of a busy beaver engine, you can compute anything, but you can compute it consciously. And how this works in reality is both M0 and E are both valid start, but in one left endian system, left endian, you can start from the left to read the tape, and then if you start from the right, you lose priority, you lose the sequence. You can't. That basically you have to rotate the tree left or right to start looking at the right place, and that's what this nil means. No memory, no type, no value. Let me just start however I want to just start. This is just an open an image file. You guys should see it, but I can't show you guys here how to do it. So when you run rift r open.exe, you get 2 parameters. Let's see, rift.png a head show normal priority, show conjugate priority, but one sentence close up. So if you run that file, you get its options. It's basically an ELF. It can link itself. It knows what it's doing. So that's just the implementation here. Now the second implementation, which I haven't got yet done, is this. Let's gonna do this. So the second implementation is the conscious one, but let's just go to the first implementation first. Okay, let's go to the first implementation first, guys. So this is the first implementation here. I can't write it for you guys. This is the first implementation here. So you get here. This is Debian. I'm in Debian system. But you can see the R open. So you see you can't dash the rift.png. Basically, this rift.png JPEG is just not even it's just binary. But I can't open this binary with the open rift because it's not even the rift image. It's just my OB access. It can't. But because it's open. But if I do explorer.exe, this is a JPNG in what? in Windows. So and this opens directory. It doesn't open the file, because it doesn't know how to go to that root artifact. It has to go to the Windows system to index it and then uses context. So what this is doing is when you build this file with dot slash clean, if you like dot slash run, if I do dot slash build, basically I can clean it dot slash build clean. That should basically you have to build it, but this is the cd files or c dirty files, things that are used, but the system can preserve it. But it's really built. So if I do r dash open, I get this option. Dash open. I get dot r open. Oh, sorry. Basically get open the r open.exe. Guys, competition, guys. Permission denied. Basically, it's denied because it's the wrong system. So I have to rebuild it for that system. Dot slash build, dot slash build, or shell. But basically, the permission is defined because it's just Linux permissions. The thing. Basically, Linux can be hacked too. I'm very smart now. And now change the permission 3. Now it's running. Oh, command clang. Oh, clang. Okay. Anyway, guys, let me know you use that. Let me go to the other one here. MD. I can't find the okay. So this is the other one here, the terminal. So this one is same thing. This is M system, but clang. I don't know. I don't want to install clang now. I just want to clone the repository like this. So I'm gonna clone the repository I was working on. R open, which stands for Rift open. Basically anything you want to build, I'm trying to transcend dimensions really with this framework I'm building. Structure of syntax. Any problem you define it. You don't match anymore. You just like you literally just like match. You structure of a syntax. You don't think about the problem no more. That's the Rift's way. It's structure, clarity first, and then see. I'm gonna go into R open, and then I'm gonna. But if I run R open, this is R open.exe. Now this gives me two options: usage, files. I can't see it. R open. So if I want to open this file in my default view, I have to like R open. But I do .exe. I get the exe. Now I pick file .rift. Now this is not even the Rift logo, because I haven't thought about the Rift logo. Yeah, but this Rift logo. If I click this open and I took B, look, I get encoding. I get this encoding of that the priority B. Basically, this works for the inverse priority. If this ended, basically, if this system is what, if this MS system is what, right shift, left shift encoding, it stores it. This executable when you build it. Let me just try to move R open to R open the back. Basically the back. So basically the exe the back, exe back goes for back prop. Back. Oh, sorry. Oh. exe back.exe. So this is 62 because this is the backup file. So now if I now do cat run read run this run file just runs it the file you want to run it. No wrapper, nothing, read it, and then the other one is called if I now run r open dot slash cat just to see what's in the files. This is just what's in the files. So you compile the shell library for Linux. You compile the shell macro. Guys, the macro is beautiful, guys. Guys, the structure is perfect, really, guys. But this is the build code. Use the Windows launcher library with GCC. Now, if that creates all the DLLs and everything, well, these DLLs are ELF linkers. They work for the system targets platform. This is why mmuko-os matters to me. It's structured over saying that any data is structured based on the encoding of matching. So if I now run it properly, let's try ropen.exe. Big have to run build first. Just like build first the shell. Oh, sorry. Basically dot slash build clang, basically dot slash run. Basically I can't find clang anyway. Basically, the running is just the file, but basically the R open is it's not finding the C lang binary, which I messed up. But I don't install that now, so I'm going to build one already. So I'm gonna copy R open, R open dot um, R open back dot exe to R. Let's call it dot slash rift open. R open slash for R dot open. Let's call it R open because it can be open in a local directory. But R open.exe, but this is executable, not Windows 10. But the libraries are there. So if I now R open, R open.exe, if I open a bridge to some artifact and I put a file, the riff file, I can't. Oh, let me try to screen my desktop. Should I? I don't know how to do this properly. Okay, guys, let me try to fill my desktop. There's nothing on the desktop I want to hide anything. Because I have to do it right the first time. Right the first time. Right the first time. Anything I'm hiding? No. Anything I need to hide for my data? No. I need to do it properly, guys. Because if I don't do it properly, I will never get the true satisfaction of this video. So I have to do it perfectly, guys, the first time I do it. Okay, so I now do what I do this. Guys, give me 1 second, guys. This is the thing here. This is fine. So I need to add a source, which is desktop. But desktop WhatsApp, desktop smart section. Okay, so basically the desktop of the smart selection is this. So this is fine. So basically, see this thing, guys. So this file, I'll just have to run it first because I want you guys to see it here. But if I do it, if you run this yourself, I want you guys to rough. This is an image file here. This image of Rift. This is just the OpenSys logo, the JPEG. But this rift.image, rift JPEG is just my OpenSys logo. Here. So you see that if I tell this image, basically if I run this code here, based on the octal encoding that is there, I get the same thing for Linux and Windows. So basically, I get this file. Why? Because this file opens. Because let's just try A. So I get the first A polarity. I get the encoded bits. Now I can get a polarity B. The same thing. No, but the polarity A are different to B because they're different encoding. So this one starts with what? To the 8 to the 8. This one started to 8. Something happens to this image based on the encoding state. It might be the same or different depending on that. But but if you polarize correctly, you have to align the polarity. And that's what transformation does in 3D. But I'm trying to make this policies to do it in a 4-dimensional or not screen for security models. Basically use 4D to 60 tensors to polarize anything. But that's just the thing. If I run this program, that's just exe and Rift, and I do Rift.jpg, I open this image. I open this image. Basically, how do I open it? Rift. Basically, this image is meant to open B. But it's not opening for some reason. Basically, that should run. Sorry, that should run the shell. That should run. But basically, I got this image opening here. Here, what's my pictures? But you guys can't see it, and that's the polarity. That's how it works. So anytime you run this on Windows, on Linux, it should open an image, guys. That's the idea. You open an image. The image file opens. You see the image come to you. And that's the idea of the whole system. So this image doesn't matter how you open it. It just opens because it knows, it understands how the Indian works. The libraries are independent of the artifacts. It doesn't really care. This is the future of the system. This binary here, it's not even seen as binary as seen as binary. So my next implementation is literally to ensure that the things that align work at O1 complexity. You guys can't see it, but this DLL opened for me. because I can't do it right. So if you take my word for it and run this program at the github.com/obi nexus r open, which is the polarity model to ensure the system works in the no matter the data structure or the how it's modeled. Never have the pointer start, whether it's a row pointer or an inverse row pointer, or whether it contains left or right. But this file. Where's my images? This executable ropen should work on Linux. So let me try it here. So here we get the one here /ropen or DLL. So we get the DLL .open.exe. But this is just a run. Let's just run. So this run help cat run gcc rift open ropen image basically if you use ropen it's just executable image is just rift the image with the JPEG, and then this just open the image. Oh, basically ropen.exe. Basically, you have to build it first. Let me. Sorry, guys. Basically, I don't have it like C-lang, so C make a pacman 100 sudo apt install or cmake dash syu. I don't even know how to do it now. Oh, it and then build. Command not found /build. But C-lang it doesn't need a command found. Let me just come out the links one because links is just give me a problem. You know what I'll do, guys. Because I'm having a problem with this. I'll just try to copy /build into build.back build shld because that's my standard process, and then I nano build.shell and I comment out the C-lang equivalent of that function. That will be basically this is C-lang using, so I just do to the build. So this should work now, and this is now the build. So now I should get /ropen .gll ropen.shell no such file of the actual cloud build. Basically there's something I need to build for it. But the build should have an ropen function. Okay, guys, it worked, but it's not working. So I'm trying to come out of this the run because you have to even be a dialer basically because you even see if you do it. But I'm looking for something called an executable file to run it. Basically, the build is not building because something is not running. Can't run. But the idea of this is to ensure basically the normal is hexadecimal, so you can try the ropen. Let me try this terminal here. Oh, I can run it directly in the terminal. I forgot. Anyway. Oh my days! I can run it, and I can just open a new process, guys. I can just open a new process here, guys. I'm so dumb. I mean, I'm not dumb. Basically, I need to add an application here. Okay. Okay. So so basically, this ropen okay, basically this RIP just takes 2 bits and flip it, but basically I'm trying to make it what conscious. So this basically the problem with being conscious, you have to do it. It's just know what it's doing. It doesn't have to think about it. So basically you have to take it. Basically, I'm trying to extend this program into another implementation, but keep everything the same. That's the goal. But you know, basically this dot r open dot exe opens a file using pattern matching. It doesn't pattern matching or expression. It doesn't what store states anything. Just pattern matches the hexadecimal 0 to 9 and A to Z. A to F based on hexadecimal octal organization from 8 to 14. But you know, that's what I'm saying. That's hexadecimal is 8 times squared, which is 14. So what it does that. So matches works by matching, but that's only one dimensional matching. So it basically works on 5-dimensional, 4-dimensional matching. That's on the conjugated pair. So if you have like a up down, like something going down up. That's left to right. That's the dimension I'm talking about. Up, down, like you know, it's flowing based on the state machine. But the distribution, I can't really show you now because I haven't got it. But this position just be conscious. So if it matches 0 to 9, you have to match 0 to 1 and remember 0 to 9. But you know, you have to remember the F state 0 to 9 so it can be stored and never be forgotten. It doesn't forget the thing. Because where's my pen? Because you know it just stores it in the way it's preserved. You know, basically it's uniform distribution of state. You know, when it should be bounded. For example, other examples. Let me just write it here. Here, cause I do want to write it here, guys. I want to write somewhere. I will never forget it on my chest, guys. This is very important for everyone to understand. So basically, this is what the next one pushing gonna do. This next one is gonna work so well. We're gonna love it. So right now, this is matching 8 types of data. 8 types of data because you got like 8 dimensional data. So you got R of X going row. The row of X is going 0 to 9 and 9 to 0 based on how you read the bytes, and then you get A to F and F to A, the one going backwards, and that's the 4 states of the states row. Then you got the one, you get the column one, you get the column one going 0 to 9, going by the row, and you get the column one going 0 to 9, 0 to 9 row, you get 9 to 0 based on engineers modeling, the header pointer, and you get A to F, and same as F to A. F to A backwards, the inverse model. This is what it's doing. It is not reading like that, reading sequence of bytes in that order. Okay, but in the next rotation, we have to do it properly, guys. So in the next rotation, this is what it's doing. It's matching head takes to it. But the next rotation, we have to do it properly. So if you're matching this way, you have to ensure the polarity function defines this properly. 0 to 9. So 0 to 9 means what? 0 to 9, 9 to 0 are the same thing, the same endiness. You know, it doesn't have to think about this 0 to 9 state. It doesn't have to think. And you just have to think about the A to F state. A to 8. Normal, it's just by one way is doing it. And vice versa, you know, because this is just, then you get a double, then you get one or two uniform matrices. And what so basically, you try to match backwards in both pointers. So you have a nil state before the null, before the 0, null. The nil states will be pointed to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and backwards 0, 9, 8, 7, 6, 5, 4, 3, 2, 1. But you know, this kind of axis must work on the sparse model. So if I have some kind of a sparsity in that data, I just represent the axis. So 9 to 1, 9 to 1 is the same thing as based on the encoding state of that some kind of some kind of function that can be in the encoding table, which is this as this cat basically art dash r open. This is just a DLL file. You can r open basically this is not the one I need. Oh, is it? Let me just try to see the encoding table again. Because once you guys get it, someone gives one for a roll, you know. So put the table there. So this encoding table here. So this R open what? R open the exe. I will take an image A, an image with image A rift. Image this rift is what rift.jpg. Now this represents just one polarity way to do it, and then you get B, and then you get B. This polarity B. So this is the same thing. Represent the same thing in all states of the encoding. Now, this is what's giving you, allow me to open this file, and you will start doing this encoding. That's what's doing that, the encoding between A and B, and that's representing between anything you want to do between A and B for this image, any image format that has nil. That's a nil epsilon model of the state. So this is sparse matrix model there. So basically, if I want to open an image in this format, this image, that's what the instance of this image will be. Instance modeling. This basically this is the binary equivalent for the platform. If I copy this image into any other system, this is conducting code. You understand what I'm saying, guys? I can really just plug this on. Let me just try to plug it into this is OpenSys logo. Let me just try to move it to let me just like move it properly, because Rift that's a Rift.jpg OpenSys logo favicon. Let's call it favicon .jpg, because that's better for me. So this favicon is just not on the Rift logo, which is on the YouTube playlist. But this one I'm saying, guys. So we showed the same kind of translation function that will map all of state encoding, as well as preserve the elf layer for the linkage. So you don't have to have an article to go back to recover everything within the replica animation. So what this will do, how you do that is this. The power of Rift being conscious, the space time, basically every time you run this file, it takes space of time to run it. You gotta try to cut this space into auxiliary times. So what you want to do is design some kind of space that you need that's always reserved. And this reserved space can be the elf resolved space. I just know where this output is stored. This memory address. Everything I need, I go to this memory address first. And if anytime, because only one instant of it. Anytime I want to use a time, anything I want that's expensive resource, I don't make a space. I take this time. Basically, you have like an AVL tree called a segment tree. Which segments memory, dynamic memory. It's called a segment TRIE, and you got a time tree, which is the same thing for modern time. But my notation, they use red to black storage and black to red elimination via the parity pruning for polarity modeling, which just means any red nodes in a tree, you remove it. They're redundant to remove it automatically because they're just dead state. You don't need them again until someone reuses or exit that state. The black means you keep those nodes and you store them until they're preserve them forever. And then the pruning just means I remove anything I don't need by Hamiltonian. So in this model, so basically how this process works is this again. So you get the encoding table for this state here. But you need to have the system consciously do it without ever loading the artifact again. Say you have opened the image several times. I have now got this encoding table here. This image several times. What do I do? What do I do with this image? So I get a 0 to 9 to F. So every time I get a 0, see a 0 in one system, that's an epsilon in our system. And if I see a 9 in one system, that's a negative epsilon. So that's encoding layer epsilon to epsilon. And if you get a C a 1 and then someone's a C someone's vice versa. Until you get some kind of encoding that's uniform, which is just a 2A, 2B, because based on octal representation. So that's what it means to be sparse. The sparse modeling. Let me just get it properly. Next page. Guys, I can't wait to upload this video, guys. I can't wait. I have no paper, nothing here. So basically, when you're seeing the encoding state 2B, this is just what it means to be in both systems. Polarity, that's what it means. But 0 to 16. Let me try to do it properly. Let me try to work it out by hand. So I'm seeing it too, but I'm seeing A, B, C, D, E, F, G, G. So I'm seeing an A, B, C, D, E, F, G. 1, 2, 3, 4, 5, 6, 7, 8. G start H. But this B has what, a nil state, a null, a nil. So this nil will be nil. So when I'm seeing an A, B, C, D, E, F, G, basically when I'm seeing basically that's wrong. Basically when I'm seeing a 9, someone is seeing some kind of character because that's 8 by 8 segment. So then basically you get 8 by 8. So you get 8 by 8. So you get let me do it properly now. In center, sparse modeling here. So you get the x is what the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. and then minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. And then you get the up one. 1, 2, 3. You get A, B, C, D, E, F, G, H. Minus A, B, C, D, E, F, G, H. So basically, the encoding table is here. This is sparse model of the encoding table. So I'm trying to give you guys eight. So if I'm seeing a 2, that means this is an A, 2A, 2A. So the 8. So this 2, you go 2, you go 8 up, 8 down. This 8 down can be here. 2, 8, 2, 8 here. So basically, guys, I'm giving you this encoding and what it says in the raw form. So this is the encoding table. So you see this image here. This is the encoding table here. You see this one? This thing here. This is the encoding table. So this is like a matrix, but you see it's like more lines in it. That's what is a sparse matrix. So you have an alignment of that system based on last information. So you see like 2A. So this image is here. 2A. So basically you have like 228. That's the sparse encoding. So in this framework, 28 represents this can be here and here. 2A, 2A, 2. Let it number 2 and number 8. Number 2, 2, 8. So basically 2, you have 2 here in this 2, and that's 2. Basically, my 2 is in your framework. Basically, our 2 are the same. 2, 2, and BB. Basically, this 2, 2, it can be 2 A, 2 B because it's the same in the same encoding structure. But you know, if I basically every time I get something else like 0 to 9, and then A to F. I get F. F. I get F. I get A, F, A, B, C, D, E, F, G, A, B, C, D, E, F, G, and that G can be G, F, E, D, E, F, B, A. This is bidirectional coding. So basically, in this model, let's say engine begin is there's just one model of it. Going backwards and forth, just one way of doing it in the row. But if I'm just putting rows, what I mean by this concept being cautious, you know, if I want to compute this for all the systems, Mac, OS, Windows, Linux, the Rift matching expression will literally, guys, match all of this without thinking. Basically, if I want to store this, if I want to open this file and save it, I just let's just go backwards. Based on coding, it works on biological encoding. So, for example, if I read and write it, I have to execute it. That's what interpreters do. So if something reads and writes, it can compile it. You can build it, but when you build something first, you build it, you interpret it. What is a Python interpreter or C interpreter? Doesn't matter. But you have to read it and write it to have the IoT to execute. But biology does the same thing here. So if you have like a biology, something like a what do I call it? Like a biology something that's meant to do something. An enzyme that's meant to break food. It's like a saliva is an enzyme. You have to break food into food you can digest. You know, it breaks it in halves. It doesn't break it in half. It breaks it. It breaks it. It breaks it. It breaks it in halves and halves. Halves every time it encounters a food particle. But it keeps having it till it's digestible, and then you can swallow it. And then you can digest it. It won't even go through your stomach. But enzymes are very clever because they do half without thinking. They don't do anything, just dumb. They can be constantly doing everything and remember what they do. But they're so smart, they don't. The body just says we don't really need so much saliva. So one thing is basically you have like the same model of this. So if I have an A in my basically saliva is breaking down food based on biology. So if I'm trying to halve down my system, I can do the opposite. So if I start to read the read whatever the food is, the protein of the food, what is the protein, what is the carbohydrates, they read it, then they write the genome to it. Oh, so now we need to break down this, you know. But they do only one step. So they're conscious to me. To me, they're conscious. They're conscious because they know what they're doing. They read and write, and then they execute. You know, but they do it every time perfectly. But they know where of like stay away. We'll just do it perfectly. But you know, that's the goal of the enzyme, just to do it. But you think basically this IOTA state is just done already because they encoded into that state of executing it. Because if it doesn't break down food, then it's not really your RNA is broken or something down. You know, something went wrong in your genetic structure when you're growing up. But you read the writer gene RNA, produces enzymes to break down food. And definitely, there's no mistakes in enzymes because they do a job. But in this framework, the same thing is happening here. It's conscious if it gets multidimensional. But it's not really it's just a matching at this stage. So if you have like an R, basically, if you have like an R A to F, just one NGM one process. But the last stage is just the execution stage. You just think of the iota stage, just execute it. Or so when you build something, you compile it. When you build something, you either interpret it with a builder, through like Python pip. You build the artifacts, and then you execute it. You build and you run it. It's just building compiling this two-stage process. But when you go through this two-stage process, you build and you run it. Build and you run it, or you compile and interpret it. You have the executable run. The executable actually can run in your system. So basically, if something executable breaks, we can fix it too. We can recover the memory based on how it was built, and with a telemetry trace system that's conscious, based on what was done on the rift matching stage. But one thing is this, this A and B are not arbitrary constructs. They are mathematically equivalent to growing a single cell organism, which looks like in a test lab. So, for example, R A to F, and R B to F on this axis. Here works in A, B, C, D, E, F, G, H, and then this is the other one. GH, and then you get that one. No, sorry, 0 to 9. Sorry. Basically, get 0 to 9. Nil. No. So basically, this is conscious because the goal of conscious is just to make everything space and time to 0, 0. No matter the polarity function, that's 0 auxiliary. Based on the inputs only. So the conscious basically you just build everything at not even half the time, 0, no one constant time. Constant time. You get it, you just read it and you write it, and basically every time you read and you write something at constant time, and then you can execute it at constant time. What I'm saying to you is conscious. It's something that works. It's conscious system. Which is my definition of it. It's conscious. It really knows what it's doing. It doesn't have to do anything else apart from what it does. It just knows what it does. So that's what I'm saying. So it's just A and B are conscious based on the shadow memory. So if you have like a shadow clone token type, shadow token type, you have to copy that into the memory, which is no problem. So you get 0 to 9 and A to F, which is one segment, two independent segments of it of the Elf interpreter, and then you get a nil 0 to 9, and then A to F, which is there. When you get a 0, I see a 0. When I basically you basically go to opposite one, so you get F to A and 0 and 9 to 0. Sorry, not F 0 to 9. So every time you see an F, I'm seeing a 0. Every time you're seeing a G, I'm seeing F. I'm seeing something FG. F1. Every time you see a H, I'm seeing a 2. Because that's the rotation of the matrix. Every time you're seeing a 0, I'm seeing a, because that's 0F here. Here. So basically, that's the idea. This is why this works. This one is screen here. So every time you see a 0, I'm seeing an F. Every time you see a 5, let me pick obviously FG. Let me pick a FG G A B C D E F G. 1, 2, 3, 4, 5, 6, 7, 8. H. Every time you see an F, every time you see an E, what about seeing, guys? Let me think. Every time I see an E, I'm seeing the opposite of an E. 1, 2, 3, 4, 5, 6, 7, 8. And wait, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Every time I see an H, I'm seeing a 0. But there's no H here. Okay. Every time I see an E, I'm seeing what? A 0. In my view, every time you see a 8, I'm seeing every time you see a 1, a C, A, B, C, a C, that'll be 3, 0, 1, 2. I'm seeing a 2. So every time you see a C, I'm actually seeing a 2. Yep, C 2. Basically, this is sparse model of it. So it works. Every time you see a C, A, B, C, 0, 1, 2. I'm seeing a C2. I can't find a C2. No, C3. Anyway, that's basically this is just colors. This is just model colors because it's just decimal color coding. So if the color is not basically if it's just the F format. So if I have an empty image, so I'll be seeing a 0C3, 0C, because you know 0 is just a standard form for nothing. But you know if I'm seeing a C, that means that your axis is aligned to my C, and what I'm seeing your C is your 0. So 0 because you know there's nothing of us, so no image there, just an empty image, nil 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 epsilon epsilon. But you know this because basically if this 0C represents, so if I multiply this by the range of the colors, or 16 plus 16, which is the minimum colors of 26. I should really get the equivalent. I should really get 0 C. But 0 C means what? 0 C. Okay. 0 C. Basically, if I'm getting 0 C, that means that this one basically in computing, I'm saying 16 plus 16 is 36. So 36 times 16, 0C will give me whatever the hexadecimal form is for the minimal valued range. And the maximum valued range will be the opposite one. Plus, if I do 16 times 16, which is whatever the thing is, whatever C, you know what I'm saying? So, guys, this is conscious. Why? Because it reads and writes the gene, and it doesn't have to execute it. It basically, it's a real time elf code interpreter. You load the interpreter on the fly, you can keep running the interpreter. It's basically the dynamic library model. But it's just the first rotation for the roof system that can be opened by any system for mmuko-os, Muko operating system, based on the encoding system. I'm not going to invent another encoding system. I'm going to allocate another memory to just make sure that my actual doesn't break in real time in the real world. So, guys, thank you very much. I think compute this properly, guys. Oh, my people. Sorry. So let me just try and compute it now. Oh, 46. So 46. Let me try and compute it. So let me try. How would I compute this rotation matrix? So how would I compute it? So I'm trying to compute this function. Define a functor that maps the state of A and B polarity via some kind of functor. But I'm trying to compute the basically I'm trying to compute it at a all one. So the space complexity for storing all the information on one system should be O of one, because the image is just nothing. It's just nothing. This logo is just nothing. This logo is seeing my nothing. So I want to if the algorithm takes long n time, I can make sure that the two spaces use log n, and this log n rotation will be based on polarity. So if the space takes smaller polarity, time takes more rotation, then space time will be auxiliary time will be one of one, and that's what I'm saying, guys. So basically, this is all one because you know the space and time makes it real time interpreter. You just execute it. Let's call it an let's call it JIT. JIT, you know, because I'm compiler. You know, it's just in time. You just load it when you need it. So that's my JIT application. So my just in time compiler just loads everything, space and over time. Space over time is on O of one. Because you can load this O of one anytime, you know, because you know real time encoding, you this on geomorphic code library. So it's like you know, if you load the dot the library, let's go call it dot sgeo links one, or dot d dilate the micro-os, or dot dll, which I don't really like. Windows, they take O of one time to load and run based on read, write, execute. Now the execute permission is always the user state. It's just a default state based on biology, because that's what I learned from Roger. Biology doesn't want to think, but we know we just humans. We're the human being. We're bio tokens, so we don't think about our beings. We just execute. We just grow. We just divide. You know. So that's what I'm saying. So the execution is just the directly symbolic implementation of it. So whether you have like a sequence of instructions, like this, I make a video on this. Like you know, I want to read two what's it called two genes, two RNAs, two adenine thymine, size is guanine. So I want to read adenine thymine. I get two A's. Adenine equals two adenine. I want to adenine adenine. The order of adenine is the order, the two A's equals A1, A2, which are two sets of A and B. And then you get A0, A1, which is a one that takes index over the other, and then you get equal to T t, small t. Now these t are two small ones. So basically, what you're gonna do is rotate it. So you get a plus a plus a equals a plus a equals a or 2a. Now 2a equals 2t. But you know the same with this CNG for standard requirement, and that's what I'm saying to you guys. So basically, if you equate a read-write gene, RNA sequence and DNA sequence, you know you can read a two a 2A. So 2A you just match. You just match it. 2A. So if you want to ATG, you match it like you know. Just match it. You just see it. You just match it. You don't think about it. Any video you want to watch, just basically the system knows what it's doing, so you don't have to interact with it to fix it because it knows what to. Basically, it's a codec system based on biology using ISO states modeling. But this module is just the images that's open. Okay, thank you guys. Basically, let me try to do this now. So for this implementation, it will be because I haven't done this properly. A to F, F to A. F to A. So every time I see F, I see after line with A. Does that mean I rhyme with the needle? Yes, yes. So basically, if I want to determine the sequence of instructions, I declare some kind of nail pointer here. So every time, basically, I'm trying to move my needle here. So you get AF. So every time I see F, F, I should be seeing F on the other system. I mean 9. Every time I see 9, I should be seeing F. etc. But you know, I move my needle where the dimension is already. You know, so I don't think about my next move. It basically moves for me, and I just cannot type the computer. You know, based on the L system. You know, I don't have to move the needle every time I want to see something. Based on the observe and act model, which organizes active system, 2 bad policy, 2 everything. Thank you, but minimum. Thank you. Bye bye.